According to Physics for Technical Students by William Anderson, there are 6 simple machines that perform a larger force of work than is applied. These machines include a lever, pulley, wheel and axle, inclined plane, wedge, and screw. These are 6 items that use physics to shape the world around us, but that go mostly unnoticed due to how basic they are in our modern world. However, just because these devices are simple does not mean that they do not serve some of the most important roles in society. It is the purpose of this paper to discuss the functionality of these simple machines and understand the mathematical principles behind how they work, along with a few examples on how they are applied in everyday life. In talking about simple machines, one must first understand the concept of mechanical advantage. Using mathematical principles, we can determine the mechanical advantage each type of simple machine will give and its efficiency. However, the efficiency is based on the actual mechanical advantage, which takes into account friction of a system, whereas the ideal mechanical advantage is only worried about the advantage of the system without friction. The ideal mechanical advantage of a system is its input distance divided by its output distance, and the actual mechanical advantage of a system is its output force divided by its input force. The efficiency percent of the system can now be calculated by dividing the actual mechanical advantage of the system by the ideal mechanical advantage of the system and multiplying that total by 100. Fundamentally, mechanical advantage is the ratio of the force outputted by the machine over the force inputted into the machine. Each of these simple machines makes work more efficient, which is an advantage. However, everything comes at a cost. Each machine has its drawbacks, which will be discussed later on. Archimedes once famously said, "Give me a lever long enough and a fulcrum on which to place it, and I shall move the world." That sentiment remains true today as it did 2,300 years ago. A lever is a rigid body where a force applied or effort rotates the body around a pivot point called a fulcrum to move a load. It decreases the amount of work needed by increasing the distance in both the x and y directions. Levers can change the force provided by various positions of the fulcrum. This gives us 3 different classes of levers: first, second, and third. A first-class lever is one where the effort is at one end and the load is on the other, and between the two is the fulcrum. Examples include seesaws and scissors, where operating one end makes the opposite end move. A second-class lever is one where the effort and load are on one side and on the far side is the fulcrum. Examples include wheelbarrows and hand-operated nutcrackers, where effort on one side makes the middle of the lever move. A third-class lever is one where the load is on one side, the fulcrum is on the other side, and the effort is in between. Examples include hammers and elbow joints, where the load and the effort pivot around a point and use the added length as a way to create advantage. This is similar to what we see in wheels and axles later on. The ideal mechanical advantage for a lever of any class is the length of effort divided by the length of the load. The longer the distance between the effort and the fulcrum, the more mechanical advantage is achieved, the trade-off being the length of the lever. Perhaps the most basic of machines, but one of the most essential, is the humble inclined plane. Were it not for this simple machine, the pyramids of Giza or the aqueducts of Rome could not exist. An inclined plane is a flat surface that has been raised on one end. This simple machine is designed to transport an object to a height that would be too heavy to lift otherwise. In its most simple form, it can be thought of as a right triangle where the hypotenuse is the slope on which the object is raised on. While the force required to move an object up the incline is lessened, the length required to bring it up the plane is increased, requiring more distance. Inclined planes are hard to miss and is one of the easiest simple machines mankind has used. As stated previously, the pyramids at Giza were constructed using inclined planes to move the heavy rock up to the top of the pyramid. Other inclined planes that are seen in everyday life include exit ramps on roads, handicap access ramps, or even gutterings on roofs. The equation needed to calculate the ideal mechanical advantage of an inclined plane is the length of the slope divided by the height of the incline. The longer the length of the slope, the easier it is to move something up to the height, but the more distance you will have to cover. According to Merriam-Webster, to cleave means both to adhere firmly or to divide. This is a good way of thinking of a wedge, which was designed to either split objects apart or hold them together. A wedge is like a small scaled-down version of an inclined plane, often pressed back to back. While it may be similar in design, however, it is not similar in function. Axes, swords, chisels, and shovels all use wedges. Armed with this knowledge, it is easy to see that the thinner and longer and thus sharper an object is, the easier it is to divide with it. Other wedges include nails and doorstops, both used to hold together or hold back other objects. The mechanical advantage of a wedge is its length divided by the height. This may look similar as it is fundamentally similar to an inclined plane. Given this as a basis, a long thin wedge will have more mechanical advantage than a short fat wedge. This is due to the fact that the large surface area of the wedge requires less force, whereas a smaller surface area requires greater force. Objects of constant width are only part of what gives wheels their mechanical advantage. To gain the full benefit of a wheel, one must use a wheel and axle. If a rod is placed in the direct center of a cylinder so that it is equidistant from all sides, but also it is smaller in diameter than the cylinder it resides in, it could be considered a wheel and axle. The difference in diameters of the axle and wheel creates a mechanical advantage. Wheels and axles are used most famously in motor vehicles, but also in ceiling fans, where a motor moves a rod spinning at a slower rate to move blades which move faster because of their larger radii. Wheels and axles can also be thought of when drawing water from a well with a crank, where the crank is fixed to a cylinder. By moving the large crank wheel, one can easily move more weight than one would normally be able to, but with more angular displacement as a trade-off. Another example is a manual screwdriver, where the large handle side is used to create a larger amount of torque for the smaller, thinner side, which can then be used to spin in screws. The math behind the wheel and axle follows the same principle as the other machines discussed. The only two variables needed are the radius of the wheel and the radius of the axle. From these two figures, we can calculate the ideal mechanical advantage as the radius of the wheel divided by the radius of the axle. Because angular velocity increases with an increase in the radius, the larger the radius, the faster the velocity. Inversely, the smaller the radius, the slower the velocity. It is through this difference the mechanical advantage is generated. It may seem more complex than others, but the screw gives more advantage than simply holding things together and ends up in unlikely places. Wrapping an inclined plane or wedge around a cylinder to form a spiral will result in a screw. Wheels and axles are sometimes used in place of cylinders, resulting in a couple of different mechanical advantages at work. Screws are used in holding things together, such as a hardware screw or bolt, but they are also useful in pushing things apart, like a trench brace used to hold back high-pressure supports and give space in between. Screws can also be used to lift, like in the case of Archimedes screw, used to pull water uphill, or in combine harvesters to push grain up a chute. They can also be found in scissor jacks, a compound machine that uses a screw in conjunction with levers to lift a car up to replace a tire. The screw's thread is the wrapped wedge that sticks out of the cylinder body. The distance between the threads is called the pitch. The ideal mechanical advantage is calculated by dividing the circumference of the cylinder of the screw by the pitch of its threads. In the 17th century, Dutch canal houses were designed tall and thin. However, the main warehouse and most valuable goods were kept on the upper floors. To transfer these goods, the Dutch used a large pulley at the top of the gable to hoist goods up and down. This helped establish the Dutch East India Company internationally and helped shape commerce for almost 2 centuries. A pulley is a wheel where the edge is used to perform the work. A groove is cut around the circumference of the wheel in order to hold a cord which is pulled around the pulley. The position of the pulley and the rope offer different advantages with different effects. In physics, there are 3 types of pulleys: fixed, movable, and compound. A fixed pulley is the simplest type. The pulley is attached in a permanent spot by the axle and the rope is moved around the pulley. An example of a fixed pulley would be a flagpole. A movable pulley leaves the pulley attached to a load while one end of the rope is attached to a fixed point and the other end of the rope is free to perform work on the system. This type of pulley is similar to a second-class lever where the load is between the force applied and the fulcrum of the lever. An example is a zip line. The final pulley, the compound pulley, offers the most mechanical advantage. By looping a cord through the multiple pulleys, more advantage is created than a single pulley alone could do. An example of a multi-pulley system would be the hoist from a crane, the resistance bands in a gym equipment, or the rigging in sailboats. The mathematics for a single pulley is only ever going to be whatever work is put into the system, so the ideal mechanical advantage is always 1. While no mechanical advantage is generated, it can still be easier to use a pulley. The more pulleys used in a system increases its mechanical advantage. Because pulleys can be arranged in any number of ways to create advantage, it is impossible to go over all of them here. However, for a block and tackle system, an equation of the total number of cords used to lift equals the ideal mechanical advantage. We are surrounded by simple machines every day, even if we do not think about it. Most of the time, we will not see one simple machine working alone, but in groups to make compound machines. A good exercise to perform is to look at the physics in life and appreciate the thought that goes into even the simplest tasks. Were it not for these 6 simple machines, life as we know it would not be possible. By studying the science behind these simple machines, mankind can create new innovations in the future. As the father of the hydrogen bomb, Edward Teller, once said, "The science of today is the technology of tomorrow." Thank you.